Hello to everyone and thanks to all the people attending the session. The work I'm presenting today regards the response in bending of sandwich panels realized with three layers composed by aluminum foam core and steel skins. The work is a collaboration between the research group of the University of Salerno and the University of Naples Federico II, as well as InnoBay Consulting. The work is framed within the issue of sustainability. We want to, with this work, to provide a contribution, developing new approaches to realize new construction products. Obviously, this is well known, this is a well-known data. The construction industry accounts for about 40% of the CO2 emissions, and in addition, it represents also negative influence in terms of waste production. The buildings, materials and construction account for about the 11% of the global CO2 emissions. Therefore, the idea behind this work is to try to provide new proposals for the development of new structural products, exploiting the new generation of materials such as aluminum foams. Metal foams are a possible solution for the development of new engineered materials. These materials are characterized first of all by the lightness, so they are lightweight materials, which optimize the strength-weight ratio and may be used to improve the behavior of existing materials such as steel. Metal foam provide a lot of benefits in terms of may provide benefits in terms of buckling mitigation and energy dissipation. They provide high shear resistance, much higher than the usual cores which are used into sandwich panels. So these materials are typically very well known for these properties, and they might be seen as very interesting materials for application in monodimensional or bidimensional steel elements, where they are used as filling materials. Nowadays, there are a number of applications of metal foams in engineering, exploiting these three properties I've mentioned. Mainly the applications are regarding the automotive and transportation sector, where they're used to exploit the lightness, also mechanical engineering, also military application, where they're using defense for exploiting the large energy dissipation. In civil engineering, there are some studies, some previous studies and some applications, but the range of practical application in structure is really negligible till now. So the idea of this work is to study a proposal which is already existing, which is the use of steel aluminum foam steel panels, where the internal core of the structure is composed by an aluminum foam core, while the external skins are made of steel. The elements in our work are joined by means of glue, of epoxy binders. We have studied in this preliminary work the behavior of a sandwich panel, which is composed by a core of aluminum foam of 25 millimeters thickness with a density of 510 kilogram per cubic meter. The skins are made of carbon steel. They have a thickness of 1.2 millimeters. The aluminum foam that we have used was provided by Saimat Ltd, Canada. The experimental tests we have executed in this work are extended to tests on the simple foam in compression and bending, as well as shear, and 3-point bending tests on steel aluminum steel panels, which were tested considering different types of epoxy binder. The compression tests were executed on the foam, referring to the transverse and parallel direction, meaning in this case transverse or parallel to the foaming direction. The type of glues that we've used have been produced by different companies. In particular, Caracol for what regards Geolite, Cicadur, in the case of Cicadur 30 is Sika, Araldite 2015 is produced by Huntsman. The compression tests, which are summarized, the result of the compression tests, which are summarized in this slide, characterize the behavior of the aluminum foam which are different in the two main directions as above said. In particular, this material provides higher resistance in the foaming direction, so in the direction which is longitudinal to the direction of the panel, while in the transverse direction they provide lower compressive strength. In this case, it was about 1/3. In the foaming direction, the resistance was of about 10 megapascal. The main feature of this material in compression is that they have a very large strain hardening capacity without any loss of resistance, and in particular they arrive basically at a point where they reach a full densification of the material with very large strains. Shear tests were also executed. The layout is very simple. The point of application of the load was very close to the support to promote the shear failure of the panel. This is one of the typical tests that we have executed. These tests were showing a resistance of the aluminum foaming shear of about 4 megapascal. During the test where we monitored also the deformations, this was done also in the 3-point bending tests, which are shown in the slide here presented. In particular, these 3-point bending tests were showing a behavior characterized by the achievement of a yielding point, some strain hardening and ductility up to the failure condition that was achieved due to the failure of the foam at the midspan. The resistance, the stress in bending, the bending stress was shown to be larger than the compressive strength of material, with a factor which is equal to about 2. This is due to the production process because the panels usually undergo also a lamination after the foaming. Therefore, these materials typically have very large resistance in bending, larger than compression. This slide here is presenting now the results of the panels the sandwich panels in bending. The tests were executed under a 3-point bending condition. In the upper part of the slide there is the experimental response, which is shown to be very ductile when we used glue with very high bond strength, such as the Araldite 2015. The panels were achieving all the same ultimate resistance, independently from the type of glue that was used. When we use large high resistance glue, such as Araldite as above said, the panels were able to provide also very high ductility. The failure condition was typically achieved due to the bonding of the steel skins, typically together with the local buckling of the upper skin in compression. Into the paper, simple analytical formulas where the accuracy of simple analytical formulas was also checked. In particular, we have checked the results of elastic and plastic analysis of the cross-section and checking the accuracy in terms of stiffness, prediction of the yield point, prediction of the maximum bending strength, and the bending moment curvature of the cross-section that was measured during the test. In particular, simple formulas were checked, referring to the elastic analysis, basically the typical formula based on an elastic analysis of the cross-section were developed, checking that these formulas typically are very useful to predict, are very accurate in predicting the stiffness of the panels and also the yield point. For what regards the ultimate resistance, a step-by-step full integration procedure was carried out, integrating the stress and strains along the cross-section, setting a procedure based on the construction or a moment curvature curve. This moment curvature curve was developed, predicting also the ultimate resistance of the panel. Also, this ultimate resistance showed to be to provide a very accurate prediction. In addition, we were able to compare the moment curvature measured during the test with the moment curvature predicted by the analytical modeling. The matching was really accurate also in this case. finite element models were also developed during the work. In particular, we have developed a finite element model through Abacus, modeling the materials with elastic plastic behavior, considering the damage initiation criteria and the damage evolution law. The glue was modeled with a cohesive contact behavior. This cohesive contact, for the definition, needs the definition of stiffness in the three directions, and the definition of fracture strain and damage evolution, which governs the debonding of the steel skins over the aluminum foam. Also, the model was providing a very accurate representation of the experimental behavior. This is both referred to the case of the aluminum foam only as reported in the upper part of the slide, but also referring to the behavior of the aluminum steel sandwich panel, which were able to provide a very accurate representation of the experimental response. The finite element model was used to perform a parametric analysis considering both geometrical and mechanical parameters. The parameter that was shown to be very important for this type of sandwich panel, as expected, was the glue mechanical properties, the glue strength and stiffness, and also the foam density. This because the foam density is mainly related to mechanical properties of the aluminum foam. In particular, the epoxy shear strength governs the ductility of the panel, as shown also by the experiments that high bond strength is typically required to have high ductility. The foam density was shown to provide a significant to be very important for the development of the strength of the panel, only when we are considering panels with a density which is lower than 300 kg per cubic meter. So typically densities should be not too small to allow the failure of the panel in bending and not in shear. In conclusion, the work has shown that the solution is very beneficial in terms of lightness and provides high stiffness and strength. The behavior of the panel is typically mainly governed by the glue strength. The failure is triggered by the bonding typically. Additionally, if the glue is sufficient resistance, the panels are characterized by high stiffness and resistance and high ductility. The panel response is typically predicted and can be easily controlled with simple design equation. I thank you for the attention. Thanks.